The starting point for this video is that in most analyses, we estimate some type of local average treatment effect. So we estimate the treatment effect for those people or units who comply with the initial treatment assignment. The question is then, how can we extrapolate from that group of those compliers to other people who do not comply? In other words, to always and never takers. For that, we need marginal treatment effects. And what I'm going to show you in this video, or what I'm going to move towards, is how we use marginal treatment effects to get towards a target parameter that is what the ultimate goal of our policy evaluation should be. So one thing to be aware of is that as with any extrapolation, going from the local average treatment effect that we actually estimate to any other parameter requires making strong assumptions, because we can only observe the treatment effect in a small range where those compliers lie, but we do not see anything outside of that range, and we have to obviously extrapolate outside of that range, and we can only do that under assumptions. And the tool that allows us to make those assumptions in a meaningful way, or that helps us doing so, is called marginal treatment effects. So what we do here is, as we've previously seen in the Heckman procedure, and also in Björklund and Moffitt's model, which is essentially a marginal treatment effects model, is we explicitly model selection into treatment. And a typical marginal treatment effect analysis is based on potential outcomes. So the idea is, for every person, we have two potential outcomes. One, what would be that person's outcome if they received the treatment, and one, which would be the outcome had they not received the treatment. And so then we again have the Roy model, whereby the potential outcome equations have a common component that is the same for everyone in the population, and an individual specific component that is individual specific and is unobserved. The goal of the marginal treatment effects analysis, besides the ultimate goal to quantify that policy relevant treatment effect or some target treatment effect, but the goal of the analysis when we actually carry it out is what's called a marginal treatment effects curve. What is that? It's a curve, so it's an upward or downward sloping curve that relates two things. So we will have on the x-axis, on the horizontal axis, a measure for the unobserved heterogeneity in the treatment effect. So think about, again, the example of lining up, or the idea of lining up people from the person with the lowest treatment effect to the person with the highest treatment effect. That's what the x-axis is. The y-axis is then, apologies, it's the other way around. The x-axis is the propensity of people to actually take the treatment, and we relate that to the actual treatment effects. Now, both these things are not observed, but we can quantify them based on reasonable parametric assumptions. Now, I will give you in a second an example of the marginal treatment effect curve that should clarify what we're doing here and what we're after here a little bit. So I will first show you the curve and then show you in subsequent slides how we get to that curve. Okay, but underlying all this is the marginal treatment effect, which is the treatment effect for a given level of x, which is an observable characteristic, but also for a given level of the likelihood of taking the treatment. So think about the simplest switching equation that you've seen, where you just have a constant gain and then maybe an individual specific cost and maybe some instrument thrown in there for good measure, something like this, right? So what we have, what the marginal treatment effect is, it's the treatment effect of people with a given level of X and also a given level of V. Okay, of the cost of choosing the treatment, right? And that so that treatment effect is obviously different between is different for people with high returns to the treatment and than it is to people with low returns to the treatment. And that difference between different types of people is what then makes the what is expressed by the marginal treatment effects curve. So another way of seeing this is what we want to look at here are the marginal treatment effect gives you the treatment effect of people who are just indifferent between taking the treatment and not at that cost level V, at a given level of cost, right? And then for some people, they require a higher reward or lower costs. And so obviously their marginal treatment effect is different from those people who require a very, who take the treatment even if the cost is very high. And so typically we observe a downward sloping marginal treatment effects curve, which means that the treatment is typically chosen by the people who have the largest gains from the treatment, which is natural, right? So here is an example from a paper by Carneiro et al. And here what they're interested in is the wage returns to 1 more year of education. How they arrive at that curve, well, they use the techniques that I'm going to present in subsequent slides, but you can read more about it in their paper. But here, I find it a very interesting, just case to illustrate what the final product of a marginal treatment effect analysis does. Now, let's start with what an instrumental variable estimator would often give you. An instrumental variable estimator would either just give you the effect of getting the treatment for a small range here, or it would give you a weighted average across all those treatment effects that are seen here, that are lined up here along that curve. So what is that curve? So here on the horizontal axis, you have the so-called resistance to treatment. What does that mean? Those with the highest values have the greatest resistance to treatment. So for them, getting treated is the costliest among everyone in the population. So let's say here the treatment is very costly, and at a value of 0, plainly speaking, it's not costly at all. So obviously those with a value of 0, they are the most likely to take the treatment. And what does the marginal treatment effect curve tell us? Well, it tells us that the treatment effects are highest among those people who who are most likely to take the treatment. Or, turning things around, which probably makes more sense, it is those people with the highest returns who also are most likely to select the treatment. And it's those people with the lowest returns who do not select the treatment. So in this case, it shows that for those people for whom education is most beneficial, they are also the people who are most likely to get a higher level degree, whatever the exact education outcome is. Now, why is this curve so useful? Well, it's useful because we can rewrite any parameter that we want, any target parameter, as a weighted average of all those treatment effects. Okay, so the treatment effect here on average is 0.4 for those with the greatest likelihood of taking the treatment, and minus 0.15 for those with the lowest likelihood of taking the treatment, for whom taking the treatment is very costly. And so if you think that you have, let's say, a distribution across all those values that looks something like that, then we can basically use that distribution to say, well, what is the average treatment effect? And the average treatment effect is a weighted average of, that is, all those treatment effects that are described by this line weighted by those probabilities given by the distribution. And so that is very, very useful, because it also helps us to think, well, what is the likely treatment effect that I get from a given policy? And that will obviously depend on who gets shifted into or out of treatment. So for example, if I with my current policy, in fact, everyone in this range chooses to get treated. So these are the guys for whom the returns to education are positive, and that's why they get it. If I then say I do an educational expansion and I want to get those people who currently are not getting that higher level of education, I want more of them to go to college and get a higher level of education. But if those people are from, let's say, this part of the distribution, so let's call this section A and let's call this segment B, then you will get the treatment effect that you get from the people in B is much lower than the treatment effect you get from people in A, right? So if it's uniformly distributed, the likelihood of taking the treatment, then the treatment effect for A, the average treatment effect would be this, and for B it would be somewhere like that. And so obviously, then if I have an expansion of education from A to B, and I get those people at that region of the marginal treatment effect curve to take the treatment effects aren't this big. And if I want to expand it even further, for group C here, it's probably close to zero, if not negative. And that's quite an important thing to think about. So if you have your study where you can exploit some policy experiment or some natural experiment, it's a useful exercise to think, well, where on that marginal treatment effect curve are you currently? So what is the segment that your instrument or your policy assignment actually covers? And who are the people, if we rolled out that policy further, if we wanted to extrapolate, who are the people towards whom we would extrapolate? And if we have a situation like this, where it's those with the greatest returns who select into the treatment, then extrapolating to those who do not select to the treatment under current conditions, but would if they had a greater incentive, we can also see that the expected returns then, or the expected treatment effects, are just smaller. And that is obviously very, very useful for understanding how to extrapolate from a given natural experiment to a broader population, whatever that broader population exactly is. And so there have been lots of recent methods papers that came out that formalize this idea. the idea itself goes back to the work of Heckman and goes back to Björklund and Moffitt and others who already had a lot of these ideas and incorporated them into models in the 70s and 80s. But it has seen a revival in recent years, mainly also because with large administrative data sets, we all of a sudden have enough, oftentimes enough data to estimate a curve like that. Right? Because obviously you need a lot of data and parametric assumptions, obviously, to actually estimate what the average or what the treatment effect is for many groups in a population. Right? So you would need to have variation in the treatment for many groups in this population and not just for a small group. And so Mokstad and Torgovitsky and several of their co-authors have recently published several methods papers that show how marginal treatment effects estimators can be used to answer important policy questions, and also how they can be used to understand the difference between the parameters we can identify and those we want to identify. Now, what they do in one of their review papers that I highly recommend to read is that they split up the marginal treatment effect in separate so-called marginal treatment responses for the treated and the control group. Okay, so the idea here is that you have a treatment, and basically M1 is the weighted average of the outcomes if units were treated, and M0 or M0 is the average outcome of the same units or units with the same level of resistance to treatment had they not received the treatment. And so these are basically two counterfactual outcomes for people with the same resistance to treatment or with the same likelihood of taking the treatment. The marginal treatment effect is basically just one minus the other. But what Torgovitsky and Mokstad show here is that many interesting parameters can actually be rewritten as weighted average of these two marginal treatment responses. And the thing is that the weights underlying these interesting parameters, so local average treatment effect, policy relevant treatment effect, average treatment effect on the treated, and so on, that the weights are often asymmetric. So the treated get a different weight in those parameters relative to the untreated. So they show then an example based on an actual experiment that was done in Africa, where the treatment was, or first of all, the goal was to see what is the effect of having mosquito nets on whether people are getting malaria. It's obviously a very important question, but you can't force people to sleep under a mosquito net. So what they did instead was they randomly assigned a subsidy with different levels. So some people get a very low subsidy, that's group 1, and then it goes up to group 4, who receive a very high subsidy. And what they also then report are the propensity scores, which is basically like the first stage, which we see works, right? So people who get a high subsidy are way more likely to actually acquire a mosquito net than people who get a very low subsidy. And based on these 4 propensity scores, and based on the outcomes they observe, they then construct not one marginal treatment effect curve, but they actually construct the curves that are corresponding to the marginal treatment response of those who were treated, and the counterfactual of the marginal treatment response of the same units had they not been treated. But that's what they do here. So again, here what we have is on the horizontal axis is basically the likelihood of taking the treatment, which so if we, I mean, this is saying it like that is a little bit sloppy, because 0.1 is not exactly the likelihood of them taking the treatment, but it's that measure is related to the likelihood of taking the treatment. So here the likelihood is very high, here it's very low to take the treatment. Okay, so these are so this is a very high likelihood of treatment down here, and then a low likelihood of treatment down there. And so what they do here is they say, well, for those people who have a high likelihood of sleeping under a bed net, what would be their malaria rates if they did not have a bed net, and what would be their likelihood if they did have a bed net, and what is then what's then the difference between the two, right? And the difference between the two here for those with the highest likelihood of taking the treatment is negative, which is good, right? Which means that using a bed net helps. And again, we can see here that for those people who are most likely to sleep under a bed net, these are also the people for whom the bed nets are most efficient. That's what the marginal treatment effects curve, the light blue one at the bottom, tells us. And what the marginal treatment response functions at the top here tell us is how this marginal treatment effect comes about. Right? So it comes from subtracting, in this case, M1 and taking the difference between M1 and M0. All right? So in other words, if that person or a person of that type who's very likely to take the treatment slept under a bed net, that would be their likelihood of getting malaria would be at that level of M1, but their likelihood of getting malaria would be a lot higher if they did not sleep under a bed net. And the difference between those two is the marginal treatment effect, and that's exactly what we see here. Okay. And now what they do based on their instrument and based on extrapolation is they say, okay, what is the marginal treatment effect for different groups? And we can see again that gap between those two is getting smaller, which is also reflected in this curve here getting closer to 0. So again, if I design a policy where I distribute bed nets for free, or where I give people incentives to take bed nets, it really depends. The effectiveness of that policy depends on who are predominantly the people who my policy shifts into the treatment. If these people are somewhere around here, then I have huge effects, right? Because I give them the incentive, they are likely to take the treatment, and they have then a high return from that, and malaria rates drop. But if my policy, either deliberately or just because of the way the policy is and who responds to it, targets people on the right-hand side here, then we're actually in a situation where the policy is not very effective. The effect is not 0, but it's a lot smaller let's again call these people A and call these people B, but the effect will be a lot smaller of the exact same policy. And that's important to know. Right? That is obviously, again, it depends. Maybe anyone up to a level of treatment choice of 0.5, whatever that exactly means, most people have anyway selected into treatment and are using bed nets. And maybe there is still some huge externality attached to other people using it as well. But still, the first order effect, that is the one shown here by that light blue curve at the bottom, is a lot smaller in segment B than in segment A. Okay? And so we've seen the marginal treatment responses, which were those in here. So for the non-treated and for the treated, what would be the actual the average outcome, and then we can use those and express the target parameter as a weighted average of those two. Right? So here we have the untreated, and we take, in that case, the green line here at the top. So this would be the line of the untreated. And suppose the distribution for the untreated looks something like that. So they have a higher mass on the right. Then I simply take all the values of the green curve and I weight them by the density of that green function. Okay, so you have the weights here. And the same then I do for the yellow line here with the distribution underlying the yellow line. So let's say the distribution is more like this, where you have a huge probability mass at low values, and then you would weight all those yellow dots along the line with the density from that distribution. And then the sum of those two is the treatment parameter of those two expectations. Now you may wonder, like, how come we add one to another? Well, because those weights can be negative. That's the reason. So typically the weight of the untreated is negative, but just by construction. Or you could also say all weights are defined positively, but we take the difference between the expectation for the treated and the expectation of the untreated. Makes no difference. That's just what they have chosen. And so here are what they give in their review article, and what they do very nicely is to say, well, how can various parameters be expressed as in terms of those marginal treatment response functions, just by using those weights. And so they give here the weights, and you can see that in many cases here they are actually symmetric, right? So the weight for the untreated here would be just minus the weight for the treated. But there may be they also show examples in the paper where they are actually asymmetric. Right, and so that is obviously something that, depending on what policy you want to evaluate, is something you want to know, or at least you want to have in your head. You will see when you look through journals, you will see that there are actually not so many studies that do a full-blown marginal treatment effects analysis, because it requires a lot of data. It's complicated, but what's important here is, even if you don't perform a marginal treatment effect analysis, you still need to know what's behind the parameter you estimate and how far away that parameter is from what you would want to estimate ideally. Now, here is the example of their randomized experiment with bed nets. Okay, so this is here at that level we have a low subsidy, and at that level we have a high subsidy. And so people are randomly assigned one of those 4 levels. So I can obviously then compare people who got a level 2 subsidy to those with level 1, those with 2 and 3, 3 and 4, and obviously also any pairs. But let's stick to the comparisons of always, the lowest to the next lowest, number 2 to number 3, and number 3 to number 4. And I will show you why in a second. Now, again here, the horizontal axis is just the likelihood of selecting into treatment, which again is high here and is low there. And what we then see is the average treatment effect, and the average treatment effect here is normalized to 1. So it's normalized to 1. That's just here, and you can see here immediately. So what that shows you is basically, apologies, it's not the average treatment effect. It's the weight of the average treatment effect, and that's normalized to 1, which means what this graph shows you is what weights we apply here to get this target parameter. Okay? So for the average treatment effect parameter, we give every unit in our sample the same weight. Yeah? For the average treatment effect on the treated, if we have selection into treatment that is systematic, such that some people are more likely to choose the treatment than others, we see here that we have a greater weight on those people who are most likely to select into treatment. The average treatment effect on the untreated is exactly the opposite, right? So here, the people who are least likely to get treated, they get a higher weight than those people who are most likely to get treated. In other words, that shows you that the distribution of the unobserved heterogeneity in the treatment choice, or roughly speaking of the likelihood of taking the treatment for those different groups. And that the weight for the untreated, for the average treatment effect on the untreated, is that those groups that are least likely to take the treatment get the highest weight. And then comes the local average treatment effect here, which, remember, only shifts a couple of people into or out of treatment. And so therefore, it, rather than covering the whole support of this of the x-axis of the likelihood of selecting into treatment, it only covers an ever so small range. So for example, if your subsidy shifts these people into treatment, so before the subsidy, only those people between from here to here would have chosen the treatment. Now with the subsidy, the range gets extended by B. Then in that local average treatment effect that you get here by comparing the outcomes, in that case whether they get malaria or not, from those people who would have been treated under 1 and those people who would have been treated under 2, you get you have a massive weight for people who for exactly those people who are getting shifted into treatment. And the same goes when we compare the people who get a subsidy of 2 and a subsidy 3, and also the same goes for people who go from 3 to 4. why the red line is lower than the green line here, that has to do with the underlying distribution. And this, you'd have to read the paper, right? But what I wanted to get at here is that the main point why I'm showing this in the video and in the lecture is the following, that you see here at the bottom the typical target parameter or parameters. So let's say that the target parameter is the average treatment effect. That gives everyone equal weight, whereas what you're identifying is maybe you have an instrument that shifts everyone from 3 to 4, so shifts people between in this segment into the treatment. And so obviously that estimator has very different weights and identifies a very different parameter relative to the average treatment effect. And so that's something to keep in mind when designing your own study. So the summary of this video is that, again, it's important to know what your target parameter is. No one can take the thinking off you. But marginal treatment effects is a useful tool to actually putting some structure onto that parameter and rewrite it as a weighted average of things that we can actually observe or can observe or can extrapolate to based on assumptions. Namely, the marginal treatment effects of groups with different likelihood of taking the treatment. Now, here's a general word of advice. When you do econometrics, understanding econometrics, especially this branch of econometrics that we're doing here, causal inference, is mostly about understanding weights. Most, if not all, estimators work like a funnel. We put data in and we condense them into one or a couple of numbers. So these estimators are weighted averages of the data that you put in. And it is obviously not hard to understand what an average is. What is hard is to understand what those weights actually mean. And if you understand what those weights mean in the procedure that you're using, you're way ahead of lots and lots of people who also perform very good econometric analyses, but who may not know that, right? Because you will get an analysis, a product that is more meaningful, because you can connect it to a target parameter that is the one that you should actually be interested in, right? And so marginal treatment effects is a way of putting all these things together. This is not the summary of the entire lecture. There's one more video to follow in which I show how we actually get from the observed data to that marginal treatment effects curve. So far, I've just shown you that we have the marginal treatment effects curve and we have weights, and then different parameters are different weighted averages of that curve. But I haven't shown you yet how to get to that curve. And that's what's going to come in the next video.